Good afternoon. Welcome to the Arctic Research Consortium of the United States, ARCIS, where Arctic research has connected since 1988. And if you don't know me, my name is Bob Rich. I'm the Executive Director. Thank you so much for coming to our 8th Arctic Research Seminar Series presentation here in Washington, D.C. and online. ARCIS has been working to connect Arctic research since 1988 across boundaries through communication, coordination, and collaboration. We're a nonprofit consortium of organizations and individuals interested in advancing inquiry, discovery, and understanding of the important region and informing sound decision-making. This seminar series is designed to provide unique access to some of the leading Arctic researchers for federal officials, members of the D.C. policy community, and the broader public interested in the changing Arctic. The ideas shared here represent the cutting edge of what we're exploring and learning up north, and also what it means for the U.S. and the rest of the world. For those of you in the room here, thanks for coming out in the rain. I'd encourage you to take a look at the ARCIS materials and other partner materials out in the lobby. You feel free to take anything on the table with you. We also have, most importantly, a evaluation form. We'd love to get back, get your thoughts on the seminar and what we ought to be doing for future seminars. For those of you on Twitter, we'd encourage you to use the hashtag #ArcIsWebinar to discuss the event. We're currently joined by more than 125 registered participants online, and some of the places that people are coming from include throughout the U.S., Canada, Chile, Colombia, Denmark, Japan, Mongolia, and the U.K. So for those of you on the webinar, my colleagues are available to answer any questions you have about ARCIS or Arctic research and to forward us here in D.C. any questions that you might have for Hajo. You'll have the opportunity to submit questions at any time into the chat box, and hope to get some good questions, so be thinking about them as he is talking. Whether you're here or online, I'd like to invite everyone to become an ARCIS member. Currently, all types of organizations are eligible to become an ARCIS member if you share our vision for advancing Arctic research, and that includes academic institutions, government agencies, corporations, indigenous organizations, and individuals can join. So if you are interested, we have some applications outside, or you can go to our website at www.arcis.org and invite you to join us. I need to acknowledge our partners in this seminar series, the Consortium for Ocean Leadership, which enables us to use this wonderful meeting space. And thank you also to the Polar Research Board of the National Academies of Science, Engineering, and Medicine for their assistance with registration. And of course, I want to thank the National Science Foundation's Division of Polar Programs for major financial support to ARCIS, and which enables this seminar series. Now, without any further ado, let me introduce our speaker. Dr. Hajo Eicken is the director of the International Arctic Research Center and a professor at the University of Alaska Fairbanks in the Geophysical Institute. And he has been working in SeaIce geophysics for a long time. He's have numerous honors, which I won't go into. He's studied all aspects of sea ice, the impact, the processes, the implications for populations, and I got to know Hajo in his role that he recently retired as the former chair of the Science Steering Committee for the Study of Environmental Arctic Change, or SEARCH, which ARCIS is integrally tied into. And it's been great to work with him over the last couple of years. He's an inspiring leader, outstanding scientist, and his presentation today is titled Observations and Predictions for Arctic Sea Ice Use, Perspectives from Coastal Alaska. Please join with me to welcome Hajo Eicken.
Thanks, Bob, for that nice introduction. So welcome everybody here and online. Actually, this is going to be the first presentation I'm giving in Mongolia, so I appreciate that in particular. So what I was going to do today is give you a sort of a brief glimpse of some of the types of information that we might have to think about in terms of sea ice uses in the broadest context now and into the future. Before delving into the depths of the talk, I just want to acknowledge a lot of the collaborators who are part of this work, both at the University of Alaska Fairbanks and elsewhere, as well as funding support from the National Science Foundation. Part of this work relates to the Sea Ice Prediction Network For those of you who are interested in some of the predictive aspects, I'd encourage you to look at that in more detail. And some of this work is also part of Department of Homeland Security's Arctic Domain Awareness Center. So it's good to see DHS represented in the room here as well. So the talk I want to break up into basically 5 key pieces here. First, just briefly give you a perspective on changes in Arctic ice cover and introduce ice use. Some of you know a lot about ice use already, but given that this might be a bit more diverse audience, I wanted to briefly lay this out. Then talk specifically about 2 examples that I think illustrate well, even though they're regionally focused in Alaska, I think they represent well the types of things that we need to think about in terms of the information that needs to be provided in the future, the types of predictions, and the types of partnerships that would be need to be in place to actually pursue this type of work. And the 2 examples I'll specifically look at, one relates to the seasonality of the ice cover and changes we've observed, and the other one relates to ice stability. You already noticed that these are terms different from, say, ice concentration, ice thickness, the standard geophysical variables that you're used to. And then at the end, I'm just going to briefly try to see how we might collaborate across different types of entities and partnerships in living and using a greatly transformed ice cover in coming years and decades. So again, just as a reminder, we're here in 2016. We didn't quite reach another record minimum this summer in Arctic sea ice extent, but one of the things you'll notice is, if you look at the past few years, that there's significant interannual variability now as well in sea ice extent, and that interannual variability is even more pronounced at the regional and local level, where of course a lot of ice uses occur. So one of the things I want to be clear you take away from this talk is that even though we tend to think about the Arctic sea ice cover on the global pan-Arctic scale as something that's undergoing transformation, those transformations and the variability from year to year is more pronounced at the local level. That's a major challenge from the perspective of observations and predictions. Again, just a brief reminder of the regional picture. What you see here is in part motivation for the talk. This gives you the changes in sea ice concentration for the past close to 4 decades of satellite observations. You see that we have this large reduction in summer sea ice concentration. These are concentration fields for September, in particular in the Pacific Arctic sector, and in particular in the U.S. Arctic, which again makes this an interesting question to ask. What's actually happening with sea ice? What are some of the uses and potential hazards associated with sea ice, and how are they changing, in particular in this region, which is the region where we see the most pronounced change throughout the Arctic, not just in terms of ice extent or ice concentration, but also ice type, ice thickness, and a lot of other aspects of the ice cover. So I don't know, I mean, difficult to do show of hands online, but in the room here, who knows what the SeaIce Eggcode is? We've got one, so I have to explain this a bit more, but I thought it would be appropriate being in D.C. You know, we've got the National Ice Center here close by. This is an ice chart here that you see up on the screen that gives you last month's ice extent and a bit more information about the sea ice cover in the U.S. Arctic sector or Pacific Arctic sector here. And the SeaIce Eggcode that you see at the very top left there of the screen is a way of conveying essential information about the sea ice cover to a range of different ice users. Historically, this has been used mostly by the maritime sector, shipping, and others. And in the process, if you look at this in more detail, this very sophisticated code evolved that essentially combined key information, for example, about the amount of ice in tenths given at the very top, the different ice types, stages of development, and thickness. So those types of variables or observables are part of the classic sea ice observations inventory, and the SeaIce Eggcode is one way to convey this information directly to specific ice users. In this case, people who actually don't use ice but consider ice a major hazard, the shipping industry. And the question I'm raising is, so this evolved in collaboration between people who are out on the ice or in the ice in vessels, the national ice centers, ice observers, ice chart experts, and the research community over a number of decades. I think now we've reached the point where we're asking ourselves, what is the next thing after the Eggcode? Because in part, we see that the ice cover itself is greatly transformed. We also see that the range of ice users is much, much broader than what it used to be. And moreover, we're also seeing new ways of communicating information about the ice cover. And all those things are tightly interconnected, are wrapped up in one big bundle of questions and potentially interesting research. And that's what I'd like to explore in a bit more detail here today. But I really see that as the major challenge for the broader research community, operators and others. Where do we go from what used to be sort of the classic, well-tried and tested approach to something that's more appropriate for modern sea ice times? So first thing to keep in mind then is, if I talk about SeaIce Use, what does that actually mean? In the broadest sense, you can think of yourselves, even here in DC, as SeaIce users, because sea ice is an important climate regulator. Recent studies have nicely shown that the changes we've seen in the sea ice cover over the past few decades roughly account for about a quarter of the total greenhouse gas forcing equivalent of changes in the Earth's radiation budget. So it's a major factor in the Earth's radiation budget. But also at the local level, you have quite a bit of sea ice used by different coastal communities, industry, and of course the shipping industry or the tourism industry for that matter. So all of these groups are interested in sea ice as a material. And I want to focus in particular today on coastal communities, indigenous hunters on the ice, as well as industry, because they actually have, in some areas, parallel and sometimes overlapping types of uses of the sea ice cover. And again, from a hazards perspective, some of you may be familiar with this. I just want to remind us that sea ice is a significant hazard in the context of the climate system. You can think about it as a so-called slow onset hazard, where changes in the ice cover evolve over timescales of decades. The impacts of those changes aren't necessarily felt immediately like you would with a tsunami or something on that scale. But at the same time, sea ice is also an important element of the coastal zone from a coastal protection perspective. I'll try to briefly cover that as well. And then, of course, we have rapid onset hazards associated with sea ice, where vessels, coming into contact with ice are damaged or potentially sunk. So that's important to keep in mind here as well. And so from the perspective of SeaIce Use, you can think of the types of questions that we would be interested in terms of use-relevant observations or predictions, and that is, well, what aspects of the sea ice cover are actually relevant to key sea ice users? How do these relate to the classic variables that we determine as, say, sea ice geophysicists? And then, of course, what's the range of interannual variability or longer-term change? And how does that translate into specific questions raised in individual localities? And all of this, again, throughout the talk, I'd like you to keep in mind that in terms of sea ice use, if you think about the Eggcode, for example, the sea ice concentration Eggcode, you have in this diagram here on the left-hand side a group of stakeholders, in that case the shipping industry, who wants a piece of information related to the sea ice cover in a very clearly distilled form that directly relates to their interests. And on the right-hand side, you have the broader research community, which I am part of, that is interested in Arctic system science, understanding how the Arctic works. You may have people who have intimate knowledge through indigenous knowledge systems of the Arctic system. And what we need to be thinking about is that as we think about a changing Arctic, it's important to keep in mind that these two groups, which are traditionally separated, need to jointly work on defining the specific problem that we have in mind, and then establish, shown at the top and at the bottom, then establish the types of mechanisms that allow you to transfer information between these. And again, the Eggcode is an interesting example because the nature of the Eggcode is what it is because it was easy to transmit it through, say, fax transfer communications or other types of low bandwidth at-sea vessel type means of communication. So the question now is for us, what is the equivalent now for us that we have a much more diverse and broad array of mechanisms to convey scientific information. The other piece, again, this is just a brief reminder, is to keep in mind that with everything that we're discussing here, there is the importance of scale that we have to consider. This is just a summary showing the spatial scale associated with the different types of information needs. At the bottom and at the left, you see the temporal scale here. So for today's talk, mostly I'll be focusing at what you might call the tactics level type of information that's of interest on the time scale of hours to maybe days. Not the climate time scale here. So let's then look at a specific example, ice seasonality. And again, for those of you who haven't spent time up in the north, this animation here that's running gives you the freeze-up season, an example of a freeze-up season, and then example of a breakup season at Barrow, Alaska. Looking out over the Chukchi Sea, you can see snow starting to fall on the land. You see some snow, some waves coming in here during fall storms. And then as this evolves, you'll notice how first pieces of ice are showing up on the water there. You see some more ice, but then you also see open water again. And at some point, you notice that there's an extent or an expanse of so-called stable shorefast ice that I'll be talking about a bit more. And now we're into the breakup season here, so now you're seeing how the ice starts to melt back and melt out from the shore. So that's kind of the typical seasonal cycle of sea ice as you might see it from a coastal perspective. But you'll notice also that even later in the season, in the middle of summer, you still have some ice lingering around as well. So these seasons are not always as clearly defined, but in general terms, what you have is typically a season of ice freeze-up in advance, the so-called stable land-fast ice regime, and I'll talk a bit more about that in the second part of the talk, and then you have the season of ice breakup and the open water season. And for all these four parts of the ice year, typically you have different users. The traditional use of the Arctic, if you will, was confined to the open water season. That's where you have a lot of shipping, a lot of resupply of coastal communities. Industry, as I'll illustrate here in a minute, did use the stable, or continues to use the stable land-fast ice part of the season as well. And then the transition seasons are actually quite important for coastal communities from a subsistence perspective. But they're also very seasons of significant ice hazards. And so these types of seasons are well defined. You just saw this on in the animation here. But if you look at this in more depth and ask yourself, well, let's just pick the freeze-up season, the start of ice appearing. What do we know about changes in time? Things start to get more complicated, in part because you have to be very clear about how you define freeze-up. So what you see here is a timeline from 1950 through 2014 that gives you the freeze-up in the Barrow region for the different years, but you'll notice that there's a big scattering of points here. The blue dots, for example, or sorry, the blue triangles are freeze-up season defined by the National Ice Center as the last day of the navigation season. And then you have on the right a mix of community-based observations by local ice experts. You have so-called persistent ice that you, again, obtain information on from local observers or from a radar sat, a synthetic aperture radar. So you see that there's a broad spread of what is the onset date of freeze-up. And that's an important point to keep in mind, that the clarity that's required with regards to defining a specific ice use is the first step in making sure that you're actually collecting the right information. And as an example, Bureau of Ocean Energy Management a couple of years ago during the Chukchi Sea exploration campaign of one of the oil majors, there was quite a bit of discussion about what defines the end of the operational season, which is defined by Freezeup, which you would think would be easy to locate to a specific date, but actually turned out to be quite a challenge to define that. And I think we're still struggling with the aftermath of trying to sort out how these seasons are defined. Another way to define them is, and of course that makes it already much more complicated, if you talk to local experts, shown here are Joe Levitt and Billy Adams from Barrow, two Inupiaq sea ice experts who've been doing ice observations with our group here for a number of years. And if you look at local uses, this is shown here for the sea ice season of 2014, you see that there's a number of other events that local users care about that are important at a much more fine scale, whether it relates to, for example, a breakout event that's shown here, and I'll give you a bit more detail on that here in a minute, or whether it relates to the presence of ice during the summer period. Or for that matter, you can see here 31st of July, ice gone at the shore and up to 1.5 meter swell on the shoreline. So these types of observations give you a very different, much more granular picture of sea ice. And what we've done is look at two things that I just want to briefly illustrate the types of observations that may be required to get at specific ice uses or ice benefits. The first illustrates a key aspect of the freeze-up season. So what you see here on the right is a photo of a so-called ice berm that Billy Adams took last fall during freeze-up. Those berms form on the beach from frozen slush that gets thrown up on the beach or forms in the nearshore zone. And in this case here, you can read Billy Adams' observation at the bottom here. This is a 4 to 6 foot high berm. Those berms are actually quite effective in mitigating or minimizing impact of coastal storms on the shoreline. And there's areas in Alaska where these berms can be tens of feet high. They also, in those areas, are potential obstacle that people actually have to cut trails through. So the question is, and of course these berms, as you can see here, 26th of October, these form at the very, very early start of the freeze-up season where satellite information may not even get at what you're seeing. And I'm seeing John Farrell's in the room here, and he's already disrupting the presentation. So please ask your question.
Yeah, thanks. I'm just curious, there's persistent ice observations by Craig George and Joe Levitt, both at the same time, and there's a fairly big spread between. Is that just expert observation difference?
No. So we looked at that in detail as well, and that depends on which location you look at. So these
in
are
Barrow.
Yeah. Well, no, but in Barrow, so that gets at another point is location. Are you looking at the Elson Lagoon? Are you looking at the area near Point Barrow, Nixirok, where you have a protected area, or are you looking right off the town? So this is not uncertainty associated with observer errors, but it's really location-based. So that's an important point to keep in mind.
Since John's already disrupted you, do you have a pointer on that? I'm having trouble. Where is this frozen slush berm in that picture?
So I have to apologize, and the way this is set up here, I'll show you. So this here, that's the berm.
Oh, okay. I was looking down.
Yeah. So if you want more pictures of ice berms, I'd encourage you to visit the Observer database, actually, where we have a lot of these photos accessible online. The key point I wanted to make is, so let me just, I'll make this short in the interest of time. So what we've been able to do in collaboration with these coastal observers at different locations in Alaska come up with a conceptual model of ice berm formation that then identifies what specific variables do you need to track in order to be able to potentially predict ice berm formation from a National Weather Service perspective, or look at is the likelihood of berm formation increasing or decreasing at different communities. This is part of a collaboration with Laura Eckers-Medrano at University of Victoria, David Atkinson, and others, and I worked on this. I'll spare you the details, but the key point is that a lot of those variables that you're interested in are actually extractable from weather records, but in particular with respect to the state of the ocean, you need to have this at a high resolution along the shoreline. So that's a potential challenge. But the benefits are significant because in those communities where you see these types of berms forming, you have a much reduced impact of fall storms compared to any other type of man-made revetment that you would build. The other point I want to briefly highlight here before moving on to the second part of the talk is, well, seasonality. We've talked a lot about this on a smaller scale. What about the larger scale? Part of the data points that I showed you in the previous slide came from passive microwave satellite data. So we've done some work to essentially apply the use of SeaIce in coastal communities and the types of rules or ice conditions associated with specific uses to define a SeaIce freeze-up date that is based on ice use rather than just a standard ice concentration. And of course here the spatial scale is much larger, so each individual pixel here extends over tens of kilometers and not just a few hundred meters. But what you see here in the next slide is a typical seasonal cycle going from high ice concentration between 90 and 100% down into the low ice concentration part of the year, and then climbing up again out of the summer up to higher ice concentrations. And so we've defined both a breakup season and a freeze-up season based on local ice use. And if you look at that, one of the interesting things that you can do then is to see, okay, how has that aspect of breakup or freeze-up changed over time, and how has the duration of those seasons changed over time? So that's what this slide shows here. At the top, you see breakup, which has a tendency to occur earlier in the year, as you can see here for the time series from 79 through 2014. And then at the bottom, you see the freeze-up, which is starting to occur later in the year. And one interesting question, that you can ask is, of course, well, where does this lead us? I'm not necessarily a proponent of extrapolating trends into infinity, but it does raise an interesting question. I mean, you see that at some point later in this century, these lines intersect, but really the key question is, as we move towards a time period where freeze-up occurs later, breakup occurs earlier, what is the nature of that winter, so-called stable part of the ice season like? And what do we know about the types of processes that currently are not necessarily part of that winter season that may be encroaching both through earlier breakup and later freeze-up? That's a very interesting, important question. And I'd like to explore that in the second part of the presentation, where we're looking at ice stability. So ice stability is, you can define it in various ways. I'd like to just illustrate this with this example here of Shorefast SeaIce at any location really in Alaska. This is more specifically Chukchi Sea coast, where you see at the top end you have the land that then transitions into a floating ice cover that's firmly attached to the shore. And then at the margin of that landfast ice cover, you see these lines of ridges extending parallel to the shore and actually anchoring the ice cover on the seafloor. And then seaward of that, you have the actual floating ice pack or drifting ice pack. And you also notice here, shown here are the Inuktitut names of these different ice types. So there's a long history of ice use, of course, by communities in coastal Alaska, and a lot of insight and familiarity with different aspects of the ice cover. So what I want to explore now is use of SeaIce as a platform, one very specific use, which is important to coastal communities from a hunting perspective, but also important to industry, who puts in ice roads into shorefast ice in coastal Alaska, but throughout the Arctic, really. In coastal Alaska, these ice roads are important because a lot of the wintertime operations associated activities at the North Star production platform in the Beaufort Sea, for example, are done through ice roads. Hilcorp now has an exploration plan that's under review that would use some of the Shorefast ice in the Beaufort Sea also for exploration purposes. So these are important. The stability of Shorefast ice, the presence and persistence of that Shorefast ice and its morphology are important aspects of ice use in Alaska's Arctic. So we've looked at this over a number of years at the Barrow Sea Ice Observatory that you may be familiar with. And again, if you visit some of those websites, you'll find data and near real-time observations from that area. We've worked with a number of colleagues, including colleagues from Japan who've deployed moorings in the area jointly with us, but in particular a long partnership of working with the local community on different aspects of the sea ice cover. So typical ice use in that area includes the development of trails. You can see a trail here in the upper left panel cut through the ice. If you look closely on the right-hand side, superimposed on a synthetic aperture radar image, you see some trails for the 2008 Barrow ice season along with ice thickness. And on the bottom left, you see a photo of Matt Druckenmiller, who did part of his PhD research on the topic that I'm going to be covering here now for the next few slides. And the stability of these trails is important, or the stability of the ice cover that the trails sit on, as you'll see in this animation here from our Barrow Ice Radar. This is from 2014, the season where I mentioned earlier, Billy Adams, Joe Levitt reported this early season breakout event. You can see how part of the Shorefast ice cover breaks away from the shoreline, drifts away. This radar system here is tracking ice movement in near real time, so you see superimposed ice velocity vectors that are generated by that system that give you an indication of the direction and speed of ice movement. But what's important to keep in mind is that, of course, and you'll see this in a minute here as this other piece of ice comes into view, that this ice, because it's being used, you typically always have people out on the sea ice in spring. And in fact, there were people on the floe that you see in view here now that were pulled off of the piece of ice by a local rescue crew with boats because conditions were such that you couldn't launch helicopter at this time. So the hazard of having ice break out like this is a significant aspect of, if you will, operations, wintertime operations by coastal communities in Alaska. So what I'd like to now do is just briefly look at what do we know, or what type of information do we have to acquire to learn more about ice stability? What do we have to track in terms of ice stability? And what would a prediction system that would look at being able to predict these types of breakout events on time scales of maybe hours, what would that look like? And to help illustrate this here, just again a schematic of the types of events that we're considering, the so-called breakout or breakaway events, where either you have a grounded ridge that sits on the seafloor that floats off, or you have parts of the sea ice cover that's attached to these grounded ridges breaking off and floating away. So the work I'm reporting on now is a combination of work done by Matt Druckenmiller for his PhD research and Josh Jones, who did a master's thesis on this. And one key question that emerged very quickly is, what is the grounding strength of these ridges on the seafloor? And in order to look at that in a more tractable sense, you're really examining at what point is the shear strength of the ridge that is provided by grounding in the seafloor and its internal strength, at what point is that shear strength surpassed or exceeded by the stress put on the sea ice cover by the force and action of winds or currents? That's really what determines whether the ice is going to break out or not. And Josh looked at a number of specific examples where we have good radar coverage. So here's one for March 2010. You see the breakout event here that's running in a loop here in the background in the latter part of March. And essentially, part of the research that was looking at these breakout events then consisted of examining the weather records to get at the wind forcing, examining records on under ice and ocean currents and water temperatures, for that matter, obtained from moorings that were deployed in collaboration with Hokkaido University in Japan in the footprint of this radar system, and of course using both local expertise and the radar and other in situ measurements to piece this together. And just as a brief summary of that story, what you see here is a time series for the month of March of, shown at the very top, water temperature, and then the seaward or shoreward current strength. Second panel, the third panel gives you the alongshore current strength, and notice that on the alongshore current strength, the maximum velocities are on the order of 1 meter per second. So this is a strong current, and at the bottom is the total sum stress on the landfast ice. And you'll notice, I mean, the key point here really to look at is that you see two peaks in the stress on the landfast ice. The red line here that you see on the right corresponds to the Shorefast ice breakout event. And you might ask yourself, you could postulate, well, if this event here was associated with a high enough stress to dislodge the ice, why wasn't the ice dislodged here? And the work that Josh conducted showed clearly that the sea ice cover has to be preconditioned for these breakout events, where you not only need to have significant or sufficient current strength, but you also have to have a history of sea level variations that essentially pre-compact the ridge as the sea level drops. Sea level rises again with, say, the tides or sea level surge, and allows the ridge to partially detach from the seafloor. So it's the sequence of set down and set up events that allows then the current to sweep the ice out, or the wind if the wind stress is significant. So you can take all of that information and ask yourself, okay, is this something that we could turn into some type of predictive system? And while we're quite a ways away from that, I just want to sort of give you an illustration of what that might look like, again, because it may also be an illustration of the types of partnerships or types of collaborations we would have to look at to get at this type of information that's relevant for ICE users. So this here builds on work that Matt Druckenmiller did for his PhD thesis, and that is to use so-called fault tree analysis as a way to consider the failure of shorefast ice, the breaking away of shorefast ice from the shore as a specific event, and we're trying to trace back the various factors or drivers of this event, and ultimately, of course, we'd like to be able to at least assign a probability of this event occurring, or even better, be able to predict it. And so what you see here is one specific fault tree where you have the shorefast ice failure at the top, and then you can trace back a path. In this case here, this goes back to a specific breakout event where the ground ridge is actually destabilized and moved out with shorefast ice. And you see the contributing factors lining up along the margins here, one being the offshore wind and the offshore current stress. Another factor that falls more into the preconditioning aspect is the overall roughness and shorefast ice extent, which of course determine part of the stress here. And also, very important, the insufficient anchoring strength. If you have grounded ridges over large areas, then even high wind or current stress may not result in a breakout. And using these types of fault trees, you can, or using the fault tree approach, you base this on so-called event trees, where you examine on the very right-hand side the probability of failure, and on the very left-hand side you have one key driving force, that is the offshore wind component. And you represent in this event tree here various cases for varying wind speeds, varying stability of the ice cover, other preconditioning factors such as sea level variations, and ultimately the probability of failure. And once you have climatological data, for example, for a given season here, again, this is now for the time period of the breakout event that we just looked at, the March through May wind rows, you can arrive at a probability of wind speed or wind stress in the direction away from shore. You can take information collected from our coastal ice radar system to get an idea of the stability, inherent stability, and the preconditioning of the ice cover. So the dark squares that you see here are areas where there's a high probability of grounding, and depending on where these and how these are located, that's going to determine how the ice cover is prone to breakout or not. And then based on that, you can actually arrive at specific probabilities over a given time period of breakout events. So it's these types of variables then that you would have to focus on in terms of providing information that's relevant from an ice use perspective. And you can see some of these are standard meteorological variables such as wind speed, wind direction. Others are such as, for example, ice roughness or the anchoring strength are variables that currently require more detailed targeted observations, but potentially could be obtained through other types of remote sensing data or modeling output for that matter. So as the final piece of this second part of the talk, I just want to give you a glimpse ahead. I already mentioned remote sensing data. Well, what might remote sensing data help us with in terms of assessing ice stability? So here I'm showing work by a PhD student, Oliver Damon, who's working with us on this. Oliver looked at interferometric synthetic aperture radar, which allows you to extract information about small-scale motion. So what you see, and I'm not going to go into the depths of this, but if you look at the top panel here, you see a stretch of coastline. You see an arrow pointing to the North Star Ice Road. North Star Island is an offshore production platform in the Beaufort Sea. And there's an ice road that goes out there that's used for resupply operational purposes. That's put in as soon as the land-fast ice cover is stable. But given concerns about stability, the question might be asked, well, what do we know about stability of ice in this area? The density of the fringes, so if you see these fringes here, each cycle, each full color cycle here corresponds to a wavelength cycle. A wavelength of the particular radar instrument used here is 23 centimeters. So every set of fringes here in this image corresponds to movement of the ice surface, other things being discounted, on the order of a wavelength over a time period of about 40 days or so here in this example. So these are satellites that orbit at fairly, or the sampling rates are fairly low, such that you can look at long-term small-scale deformation of ice. And Oliver's work focused on developing an inverse model that allows him to extract more detailed information about the type of deformation that occurred. And so what you see at the bottom here is a synthesis of that type of information, where what you see now on this color scale here is the number of events where the yield stress or the strength of the ice has been exceeded as a result of this deformation. So areas that are red are highly likely to incur formation of cracks or failure events of sea ice. Areas of blue are extremely stable. So you can use this in a way to map a key aspect of ice stability. Again, this is greatly simplified from the perspective of potential outcomes of this work. I'd encourage you to follow Oliver's work throughout the remainder of his thesis. He's got some interesting findings here down the line as well, is my sense. But right now, this at least gives us a glimpse of the type of satellite information that we might want to rely on as we think more about sea ice predictions and sea ice tracking from a user perspective. So then, to conclude, just a few words on how do we put this together. I started out by saying, well, we have these two, or maybe even several camps of researchers. You have people, or rather you have sort of ice users on one side here, represented by the green stakeholder circle, people who actually live with the ice or are very concerned about specific aspects of the ice cover. You have the research community on the right-hand side pursuing Arctic system science, trying to understand how do various components of the Arctic system or the Arctic system itself work. You have indigenous knowledge holders who have an understanding and a relationship with the sea ice. But in order for us to address, in particular, ice observations and predictions that are relevant for sea ice use, we need to work on jointly defining the problem. What specific aspect are we interested in? So here the example, for instance, would be as you define Freezeup, the definition of Freezeup and the actual data for Freezeup might look very different if you're an oil company that is required by the regulator to move a vessel off of a specific position by a certain date without the presence of ice, or if you're a local in a coastal community who is comfortable walking on even 4 inches or 3 inches of sea ice to retrieve a seal. And those types of differences are quite important and in my mind, interesting area to do additional work. The other key aspect is at the bottom here, how do we exchange information and convey or make sure that this is not just or that this actually is an iterative cycle here, and that requires quite a bit more thought about sort of modes of communication of science information. I'm encouraged to see that the search program has something on the agenda for the AGU to look at these communication pyramids. Us as a research community thinking more rigorously about communication of the work that we do, I would argue is going to become more and more important. I'm actually going to just, in the interest of time here, I'll flip through this briefly, but there, of course, as with everything, there's a whole theory underlying this here. In this case, I would argue that the theory of co-management in the broadest sense, in particular put forward by Fikret Berkes at University of Manitoba and others, is a useful way to also think about co-management of scientific data, co-management of information. It comes with specific requirements, specific frameworks, but I'd be happy to discuss that a bit more here in the remaining time. This is just again another run of the breakout animation that you've seen, but now shown in red is the location of one of the moorings that was deployed in collaboration with colleagues from Hokkaido University. And the site of that mooring was chosen specifically by input from local ice experts, and in part it was, instruments weren't necessarily placed there, or were placed there with a certain reluctance, simply because these are actually quite dangerous places to work in from the perspective of losing instruments to ice action. But having instruments in that location that was jointly determined turned out to be very important for significant parts of this work. So this type of collaboration, also exemplified here by these observations of the seasonal sea ice cycle, are important. But thinking more about the types of information products that are then shared with ice users is important as well. So what you see here on the right is one of these seasonal ice trail maps that our group has produced here over the past 10 years or so in the community of Barrow. There's a photo here of Oliver Damon and Price Levitt looking at one of these maps. So making sure that the information that's put out is in a format and in a form that is digested by or digestible by local users is a very important aspect of this as well. And that doesn't mean dumbing it down. A good example here is this one-page flyer that was produced that basically summarizes some of the work that we've learned with respect to ice movement and predominant ice movement at Barrow based on the radar and the mooring data that was shared with the broader community. So in conclusion then, what are the key points here? I would argue from a sea ice perspective itself, the changes in ice seasonality and ice stability really are an important aspect of the ice cover that as we see reductions in summertime ice extent, we need to pay more attention to. And this question of where and how do the breakup season and the freeze-up season intersect is a very important one. In the middle of the slide here, you have a few more specific points on how we can work on producing information that's more useful from a CSUs perspective. And at the bottom, I just want to highlight that from a sustained observations perspective, the Arctic Council and IASC Sustaining Arctic Observing Networks initiative, in my mind, is going to be an important element of that type of collaboration because it may help form communities of practice between ice users, agencies, and the research community. Thanks.
Thanks very much. So what questions do we have either in the room or online? Feel free to raise your hand or you can post them. John. And please, when you ask, press the red button. There you go, like John did. Yeah.
Hi, thank you. A question on the seasonality and stability. Could it be argued that we're really in the midst of a transition towards a more stable regime where you just have single-year ice and ultimately the majority, if not all, the multi-year ice disappears and that you would have a new stability because it would be the annual freeze-up and melt back? So what you're seeing now is just a transition from one regime to another, and that's why it's highly unstable, but the stability may actually increase in time.
Yeah, sorry, and that was my fault in not making clear what I meant by stability. I mean, so stability in this case really means stability of shorefast ice. I mean, I think your point is correct, and you could argue that really what you're talking about in some, well, or no, let's take a step back actually, because I think you're putting your finger on an important issue. In general, what you would argue though is that as the presence of multi-year ice provides a certain amount of predictability and, if you will, stability to the Arctic ice cover. As you reduce that, and that's what we're seeing now, you start to see greater interannual variation. You start to see greater variation at the local scale, simply because you don't have that thermal mass sitting there anymore of the perennial ice. You don't have wave damping anymore. So the ice cover as a whole becomes more dynamic, which is also shown in terms of ice, speed of ice as it moves through the Arctic Basin. So from that perspective, I would argue that the seasonal ice regime, no matter what, is always going to be one where you have a greater challenge from the perspective of predictability because you're losing one key predictable part of the Arctic. But the other point is, and that's relevant for the U.S. Arctic, is that as you transition into a seasonal ice regime, it's not, in my mind, and again, I mean, this is not, this is just based on personal opinion, I guess, hopefully scientifically formed, but my sense is that you would retain a significant reservoir of perennial ice north of the Canadian archipelago, and if you see continued advection of that ice or movement of that ice into U.S. waters, again, we wouldn't necessarily lose all perennial ice, which is significant from a hazards perspective, so that if you're operating in the U.S. offshore, even 20, 30, 40, 50, 60 years down the line, the probability of encountering thick, massive, strong multi-year ice isn't going to go to zero. That's important to keep in mind.
So I have a number of questions here online. The first one is it's from Renee Chitusco, and it's regarding the Arctic Council SEON effort. And she asks, are you familiar with the U.S. array network of stations in Alaska, Canada, and Greenland, data from which are being used to better understand the effects of surface melt and ice-ocean interactions?
Yes. and it's a great, no, and it's a good, you know, we were just talking about it as well in the context of the EarthScope. You know, we have somebody in the room here affiliated with that effort. So that's actually a great example of collaboration between different agencies, you know, in part because some of the EarthScope seismometers may give us information about coastal sea ice extent, you know, damping of waves and sort of characteristic of microseisms, but at the same time, putting atmospheric observation technology on top of these you know, seismic observatories gives you an opportunity to have better information about the state of the atmosphere. So those are the types of collaborations, and they're not always obvious. I mean, that's the interesting thing, that, you know, here you have seismologists who probably could care less about whether the wind blows or not, and the atmospheric research community and sea ice researchers collaborate. And on top of that, you know, you have a lot of people in coastal communities who say that they clearly see some connection between surges and potential earthquake activity. So there's an indigenous knowledge element to that as well.
Terrific. Got a question from Jasper Hardesty at Sandia Labs. He asks, have you made any progress with the use of ARM XS APR radar to expand sea ice detection and velocity information in Barrow?
Yes. I mean, what he's referring to is the atmospheric radiation measurement program, Department of Energy program, has an X-band radar up at Barrow and Elictuck Point. And again, that's an interesting example of the types of collaborations that one would want to pursue, because that system is set up to monitor, you know, precipitation and atmospheric dynamics. But as it turns out, if you run it in a low horizon scan mode, you can also learn about sea ice. And so that's something that we're pursuing to see whether there's multiple uses of that type of radar systems. Great.
Any other questions in here? So I have a question from Brett Craig. He asks specifically about the diverse methods of observation. Is there any more recent data? He says the last one's like 6 years old. Is there more recent data that you've collected on that?
Sorry, on which?
Diverse observation methods.
I'm not sure.
I think it was the one where you were showing the different indigenous knowledge and different pieces of information.
Oh, yeah. Yeah, I mean, there's for some of that, there's updated data. So the short answer is yes. The long answer, I mean, if you want direct access, some of the links actually in the presentation, which I'm assuming you'll post, take you to the website where you have more recent data. But if you don't find that, just send me an email.
Okay, great. Yeah, actually, all of the slides will be posted, and a recording will be up as well on the website afterwards. Question from Randy Key, and his question is, can you address what you see as under-researched areas in predicting shorefast ice formation?
Yeah, I mean, one key challenge, I think in general, this is important for shorefast ice, but for the Arctic in general, is this question of ocean ice change. I mean, traditionally, you know, we've looked at the Arctic as a place that's mostly driven by the atmosphere. You know, whatever you do impacts the top of the ice cover, and that's what's important. And that clearly is important because of the changes in albedo. But what we're increasingly seeing, and certainly in coastal locations, that's something that indigenous knowledge holders have always pointed out, is the importance of the ocean interacting with the ice cover. Specifically, what's very, very poorly understood is how much heat is actually being both stored in the coastal ocean or offshore ocean, advected into coastal areas, and released to the ice cover, melting it back, potentially destabilizing it, but also changing part of the sea ice food webs by releasing a lot of the biomass that's at the bottom. That's a key question. Over on the Eurasian side, much of that heat comes either in through the Bering Strait or in most of it in the form of solar radiation that's absorbed over the summer, mostly in open water. Over on the Atlantic side of the Arctic, there's quite a bit of heat inflow from the Atlantic water, and again, there the question is how is that water interacting with shorefast ice? That's one key question, and then others relate more to the linkages between atmospheric circulation and some of the currents that are potentially destabilizing the ice cover. That's poorly understood as well.
Okay. Any other questions? So one last question then. In thinking about the effect of wind and current on the shorefast ice, how much do you look at the topography of the ice in terms of how tall it is in different places?
Yeah, so that's an important aspect, and there's this question: is the sea ice getting rougher, for example, as it changes, as it gets thinner? There's some people who are arguing because of increased deformation, the ice gets rougher, and that allows you to transfer more momentum between the ocean, between the atmosphere and the ocean. At Barrow last year, and again, this is part of Oliver Demond's thesis research, we launched a small unmanned aircraft to extract surface topography information of the ice cover, and Oliver is now looking at whether we can get the same type of information from interferometric SAR. So there's ways that you can try to extract this from satellite or in particular unmanned aerial systems, and of course the new NASA ISAT-2 mission that's going to provide very interesting data on topography.
All right. Well, thank you very much. Let's join together in thanking Hajo again. So just by way of some concluding remarks, I wanted to thank everybody for participating today. As I mentioned, the presentations will be posted. Can you pull that last slide up by any chance? Thanks. We have a annual meeting of ARCIS members. Anybody else interested in Arctic research collaboration will be taking place at the American Geophysical Union meeting on Wednesday, December 14th. You're encouraged to be there, and following that, we're having an open reception. So tell your friends in the Arctic research community to come and join us there. And our next seminar in this series will feature Craig Fleener from the state of Alaska, and he will be speaking on January 11th right here in this space. Please remember to fill out the evaluations either in hard copy if you're here in the room or online if you, once the seminar concludes, you'll get a chance to see the questions. They're coming up now. Good. And other than that, thank you very much, and have a great day. And thanks so much for participating in today's webinars.